Class, we're going to look at partial fraction decomposition technique for integration. There are many types, and so there's probably going to be 3 or 4 videos in this series. The first case is when you're integrating a rational expression and the denominator is factorable as 2 or more distinct linear factors. Distinct meaning that they're all different, linear meaning that x to the first is your dominant term. So we're going to look at integrating 1 over x squared minus 5x plus 6 dx. That's a rational term, and if you were to factor the denominator, that would factor as x minus 3 times x minus 2, both unique or distinct, and they're both linear. Let's look at decomposing that rational expression into 2 simpler fractions. I'm going to rewrite the original term as 2 separate fractions with the factors x minus 3 and x minus 2. Those 2 factors, if multiplied together, give you the original denominator back. So what we'll do is we're going to split the original term into 2 simpler fractions. Each denominator is linear, so they're going to get a constant numerator. We don't know those values, so we're going to assign a and b to be those constant values. If you multiply through by the least common denominator, and do it all the way through, then starting at the left, you get a complete cancellation, leaving a 1. The middle fraction, the x minus 3's cancel, leaving the x minus 2. And the last fraction, the x minus 2's cancel, leaving the x minus 3. Now, since we need the values for a and b, you can randomly pick x values to plug in and solve. But if you're methodical, you can realize that if you choose x to be 2, it's going to zero out that middle set of parentheses. If you choose x equals 3, it will zero out the last set of parentheses, making it a little bit easier to solve for a and b. So I'm going to choose x equals 3. And sub it into that equation just above. On the left side of the equation, 1 has no variable, so it's going to remain a 1. Three minus 2. And 3 minus 3. Three minus 3 equals 0 times b, still 0. So we get a equals 1. Okay, we're going to hold on to that value. Another wise choice for x would be 2. Subbing back into this one again, but this time with a 2, we're going to get 1 equals a 2 minus 2 plus b times 2 minus 3. 1 equals, that goes to 0, negative b, because it's b times negative 1. So solving for b, we get b equals negative 1. On our next slide, we can rewrite the original fraction such as this. Okay, so let's recall a was 1 and b was negative 1. The original problem can now be written as the integral of 1 over x minus 3 minus 1 over x minus 2 all dx. Each fraction fits the format so that it will have an antiderivative using natural log. If you take the derivative of each denominator separately, you get a derivative of 1. And anytime you can get your fraction in the format derivative over original, where the numerator is the derivative of the denominator, then your antiderivative will be natural log. Natural log's domain is only for positives. Since x minus 3 could have a negative value, we put it in absolute value. Same thing with x minus 2. There are values of x that could make that negative, but so we need to put it in absolute value just to ensure that it stays positive. And let me remind you of that antiderivative.